Okay, let's start with this next talk on day 2. It's about full disk encryption, so just to enable you to make sure nobody gets a peek on your hard drive if this hard drive will ever disappear. Our next speaker is Jürgen Pavel from Cologne, and he will give you an introduction into the necessary tools for both Windows and Linux. Welcome him, please. Okay, so thank you and welcome everyone. Let me introduce myself first, and I'll tell you why this is important to this talk. Well, I studied in America, so this is why my English is the way it is. If you have any issues with it, raise your hand, yell at me, whatever. Make yourself heard. The second part is I work as a security consultant, so my look on this is more often than not through the eyes of an enterprise. Not necessarily as a hacker. Sometimes it is, sometimes it's not. So you'll see that. And the last part is I like to play rugby, but nowadays not so much as I used to. And why is that important? It's important because I have a free polo shirt to give away. And all right, if no one gets the question, you get it. What are we looking at and why are we looking at it? So the first question is, does anyone recognize this movie quote? Okay, no one. How long is it going to take until someone Googles it? What's the movie? Can anyone tell me? What is it? No? Nope. Nope. All right, Google time now. Anyone? Nobody wants a free t-shirt? Nope. Okay, I have a backup question for that later on. It's Mystery Science Theater 3000. Okay, so we're looking at full disk encryption, and there's two ways you can do that. One is in hardware, and that's really pretty much a new thing, where you have a little device like inside your hard drive that encrypts it, and you pretty much don't ever see anything of the encryption. Or you can have a software solution that you install on your operating system or just make use of, and that encrypts your data on the CPU and sends it encrypted to the disk. So the disk doesn't know anything about it being encrypted, in contrast to the first one. Why we're looking at it is because data is at risk. Laptop theft is a pretty big issue in most corporations, and I believe in the future there's also going to be more of full disk encryption in desktops. Oops, that was wrong. Desktops and server systems in order to minimize the data lifetime in terms of when a server goes out of order, you don't have to worry about destructing the data. You just make sure the key is destroyed. So that's why we're looking at it. And what it does, like I said, it encrypts pretty much every bit on your hard disk. And that's sort of the odd thing, because full disk encryption, the name says the disk is fully encrypted, but you can encrypt disk partially, and the name really only is supposed to say that you're working on or with an encryption solution on the disk layer. You're not working with an encryption solution working in terms of like an encrypted archive or in terms of like application encrypted file. So you're working at the disk layer, and you don't have to worry about individual files. So, like I said, through hardware, and these are just the few notes that I'll go into in terms of hardware, because the software side is much more interesting. I'm sure you've all seen the USB controllers that have supposedly encryption controllers in them, and some of them are good, some of them aren't. That's just one form of how disk encryption can be done. Another one is the hard drive itself, an internal hard drive providing an encryption. And I believe there are two right now, Seagate and Toshiba, that offer this. And the way it works is the drive just offers the ATA security command that usual drives also offer, but only at a functional level. With usually drives that offer these, you can take out the platters and you can extract the information. With these specific products, you need to use the ATA security commands, provide a password, and the password is actually used to derive the encryption key. So it's much better security, cryptographic security than just a functional ATA security command for your hard drive. And then through software. The operating system provides this because it needs to work for all applications that you want to use, so it's transparent. You just have to install it, configure it, whatever, and there it goes. And hopefully it doesn't impact your everyday performance too much, because CPUs are pretty fast nowadays, and even on somewhat older systems, you don't really get impacted that much performance-wise. So, architecture, pre-boot authentication. When you have something that's encrypted, you usually expect that you have to supply something so you can decrypt it. And if the software is an operating system component and encrypts the disk, then the operating system is likely to be encrypted itself also, which means you need to supply a secret in order to unlock the disk, in order to start the operating system. And this pre-boot authentication environment does just that. It gets loaded by the BIOS from unencrypted storage. In most cases, this will be your MBR on your hard drive and some other area, because the MBR is not big enough. So with Linux, it's a little bit different. You have usually you have an unencrypted boot partition that holds your kernel, your init RAM disk, and this partition contains the logic to display a prompt to get the password, to ask you to insert your smart card, whatever. So this is sort of not really a pre-boot authentication by like implementation, but if you want to be real specific about it, but it's sort of that. In Windows, it's more like that, because in Windows, the architecture is different, and you have a proprietary pre-boot environment that does just that. It displays a prompt, takes your password, whatever, and then sets up the system so it can continue to boot. And yeah, I already said that. So the next step is to boot the operating system. With Linux, like I said, it's a little bit different. All it has to do is, once you have the password, is mount the file system that's being encrypted, and the initialization phase goes on as usual. With Windows, it's a little bit different because the operating system with the Windows kernel or the NT loader, who here knows what the NT loader is? Hands up, please. Okay, so when you start Windows, that little black screen with the little bar scrolling, that's not actually Windows yet, it's the NT loader. What that does is it really loads the NT kernel, and this little loader, of course, needs to get loaded also. So the way the encryption products do it is they use a function, the NT loader uses a BIOS function to load data from the disk. So it says, hello, interrupt 13, please give me these bytes from the disk over here. And what these full disk encryption products do is they hook the interrupt routine, and they extend it with the encryption and decryption logic. So when you when the NT loader is run, it uses interrupt 13, and because the pre-boot environment has already replaced the in13 function or extended it, NT loader loads the data from the disk, which is encrypted, but it does so transparently. Did I get this point across? Okay. So when Windows has started, it needs to access the disk and do the encryption. The way applications sort of look at it is they just write to the file system, just nothing different about it. The operating system kernel has a little component that is the full disk encryption driver that actually intercepts the data before it gets sent to the disk and encrypts it and then sends it to the disk in encrypted form. So for Linux, there's a couple solutions that do this. One is the device mapper, which is an architectural solution. It essentially allows you to use a different device than your hard disk, and this device does nothing but encrypt the data and then pass it on to the real device driver. You can also do device driver hooking, which is more of a kernel module that looks at the driver for the hardware, for the disk, and finds the right point and just reroutes the function call to itself, does the little encryption magic, and then passes back on to the driver. So it's more of a hook and inject sort of solution rather than device mapper, which is an architectural. In Windows, you have lower level filter drivers, and what these are is every Windows driver has a higher and a lower level filter driver, which is sort of a callback mechanism. It allows you to, filter stuff, to work around bugs maybe in the lower level filter driver. And the lower level filter driver is also used to encrypt and decrypt the data to and from the hard disk. So when we look at the boot process, the NT loader uses the N13 to load the data from the disk, and the interrupt routine takes care of the encryption decryption. Well, actually pretty much just decryption on booting. So the Windows encryption driver then needs to do the same work, and since it doesn't use the interrupt routine anymore because it's just much too slow, it needs to somehow obtain the cryptographic key so that it can just do the work inside its driver and be much more efficient than the N13 implementation. And this is called the key handoff. So several products, or pretty much every product, has a little different strategy to this. TrueCrypt, for example, which is an open source full disk encryption solution, and another, they sort of search for the key. They don't know where it is, but they search for it, and if they locate it by some magic bytes, then they say, okay, I found it, let's go. Commercial products usually have a dedicated memory location where they put it, and the driver just knows, okay, it's there, I'll take it. When you're talking about disk encryption, you either consider this when you set up the system, so during installation it's encrypted, or you want to add it later on. So there's the aspect of initial encryption. How do you transfer your disk from being unencrypted to being encrypted? On Linux, you have the, like I said, the device mapper, and one drawback to it is that you cannot convert an existing file system in place yet into an encrypted file system. So you have to pretty much set up a new file system. Of course, you can just write a new file system over the device mapper onto a new disk and copy your files over. There are several workarounds, but you cannot just transparently install some or tweak some configuration and then your system will be encrypted after a while. There are commercial products also for Linux that use the device driver hooking, and they can transparently encrypt your hard disk as sort of an installation step. So the way they do it is they